I'm often asked how to use high-resolution, hand-drawn sprites in Unreal Engine to create 2D or 2D 3D hybrid games. But since so far I only covered pixel art in my videos, I never had a good answer until now. Over the last couple of months, I started to look into how to get rid of issues with aliasing and blurriness when using hand-drawn art, and how to create a look similar to Ender Lilies, The Vagrant, Escape from Ever After, or Born of Bread, which are all Unreal Engine games. But I didn't do that research all on my own, and on top of very knowledgeable members in our Discord, the developers of Born of Bread, Wild Arts Games were also really helpful and shared their settings with me. First, we're gonna go through all of the related settings, and I'll give you an explanation of how each of these affects our sprites. And at the end, I'll show you the combination of settings I came up with for my 2D 3D hybrid scene and also my flat 2D scene. Let's get started. I created a new project with Unreal Engine 5.5, but I doubt much will change with these settings in the future, and they should still be valid for a long time. Many of the games I used as a reference were still using Unreal Engine 4, so I was a bit worried this might not even be achievable in Unreal Engine 5. But after trying it with both UE 5.5 and UE 4.27, I didn't really notice any big difference. I then imported a few different assets from Douglas Avila for testing, with the Cobra robot being a free asset and the Toon Medieval Fantasy pack being a paid asset on FAP. Some of these assets already came with the Paper 2D texture settings applied, but I set everything back to the default values to have the same starting point you would when you just import a new texture into Unreal. In the texture viewer, you can see that all of these are very high quality and have a high resolution, but they don't look quite that nice in-game. On the hybrid side, we can see many issues right away. Even though the edges look quite smooth and we don't see much aliasing, the colors seem to merge together in certain places and we can see clear ghosting or after images. In the 2D scene from a far distance, things don't look too bad, but when paying close attention or zooming in, you can tell that there's also ghosting and things look blurry with the lines not being sharp either. When we switch into the unlit mode here, you can also see that we get visible aliasing or jagged lines around the edges of the character. Let's take care of these issues step by step by going through all of the related settings. The first thing we definitely want to turn off are auto exposure and motion blur. Auto exposure isn't specifically related to the problems with our sprites, but it can make 2D scenes look very blown out and overexposed by mimicking the effect of your eyes adapting to changes in lighting conditions around you. In the project settings, I just look for exposure, turn auto exposure off, set it to manual and the bias to 0. Now both of these scenes just have more consistent lighting for better testing. Next up is motion blur, and even though it's getting a lot of hate, it can enhance the look of 3D games. But for sprite-based games, we don't want to use it since it will lead to some ghosting and blurriness regardless of if we're using pixel art or high-resolution hand-painted sprites. We can simply turn motion blur off in the project settings. But even after that, you might not be able to tell a big difference since we still have multiple settings on that lead to blurring and ghosting regardless. Next up, we want to turn off Lumen and related settings just to make sure they don't interfere with our testing. For the 3D scene, you could use Lumen and Nanite if you wanted to, but Lumen comes with its own risk of ghosting that might interfere with our tests, and for 2D only scenes, you most definitely want to turn it off. In the project settings, look for Dynamic Global Illumination method and set it to none. Set Reflection method to screen space, and Shadow Maps back to the regular Shadow Maps. Again, you probably won't be able to tell the difference just yet, but we're working towards our goal. Now the next setting is one of the most important ones, and it is anti-aliasing. If you're unfamiliar, anti-aliasing is a technique that helps us remove jagged lines and also helps to counteract flickering on distant objects. But there are multiple anti-aliasing methods available with different pros and cons, and we need to make sure to select the correct one. Since Unreal Engine 5, the default is TSR, aka Temporal Super Resolution, and this is not only an anti-aliasing technique, but it's also an upscaler similarly to something like DLSS. It does a great job at clearing up jagged lines, but it comes at a high performance cost, and the temporal part in the name means that it accumulates information over multiple frames. Skeletal meshes, for example, come with motion vectors that allow the algorithm to prevent ghosting to some degree by analyzing the movement. However, sprites do not have motion vectors, and this is what leads to the extreme ghosting we've been wrestling with. It does appear that there is a way to generate motion vectors for flipbooks, but it's a huge new rabbit hole to go down that will drastically affect your workflow, and I don't think it's worth going down. But I'll at least attach a link in the description if you want to read up on it. Also, since Unreal Engine 5.4, I believe we got a new setting in our materials called Has Pixel Animation. It's not intended for sprites, but rather scrolling or animated materials, but we thought that as a side effect it might also work to combat ghosting with flipbooks. And when I tried this a few months back with pixel art, it seemed to have no impact at all. But when trying it again with these assets, it did counteract some ghosting, but it still wasn't enough to make it a valid option. I also thought that bone-based sprite solutions like Spine might be able to counteract ghosting, but it doesn't seem that way, and using their sample project I also got severe ghosting with TSR or TAA. TAA or temporal anti-aliasing comes with similar issues since again it has temporal in the name and accumulates information over multiple frames. This leaves us with none, FXAA or MSAA as the remaining options. MSAA or multi-sample anti-aliasing is a pretty old school technique that relies on detecting edges of geometry. And one of the main reasons it stopped being used widely is that it's incapable of applying anti-aliasing on things such as normal maps or shader-based effects. And since our sprite is just an image attached to a quad, MSAA won't be able to do anything to help us here. And it's also only available when switching from deferred rendering to forward rendering. Okay, so that only leaves us with FXAA or none. With both FXAA and none, we get rid of the ghosting issues and also the colors merging together, which is great. But in both cases, we do get some rough pixels around the characters and some aliasing. I do believe though that FXAA does a better job at offering at least some anti-aliasing over having none. Especially for a 2D 3D hybrid, it also offers anti-aliasing for 3D objects in the background, and while it's not the most advanced anti-aliasing method, it's still better than nothing, and it's actually also what Born of Bread is using. And also Ender Lilies, which is a flat 2D game made with Unreal Engine 4, also offers some sort of anti-aliasing. And due to none of the other methods being a valid option, I believe it's also using FXAA. So what I would do is give players the option to pick between none and FXAA, but have FXAA active by default, and for now I'll also stick with FXAA for the remaining tests. The next couple of issues I only became aware of after messing around with Unity to see how things work over there regarding high-resolution sprites. And by default, my zoom scale was set to 1.3 and made things look absolutely horrible in the viewport. So when I figured out that just by playing in a maximized window with a scale of 1 already made the sprites look so much better, I thought something similar might also help in Unreal Engine. We have multiple ways to start and test play our game, and by default when we hit the play button it just plays in the built-in viewport, which is fine most of the time but makes it hard to test things at the same quality and resolution your players will experience. When clicking on these three dots, we can change the mode to the new editor window, which just opens up a new window. But the one we're really looking for here is Standalone Game. This will launch the game in an uncooked state in a new process, and while it's not exactly the same thing as testing a package shipping build, it's the closest thing we have and will allow us to catch some problems early. And on a side note, in case your sprites are super blurry here when loading in and become clear over time, that's due to texture streaming and you can just ignore it for now or skip forward to the never stream section of this video and then come back. And during my prototyping phase for this video, I also had cases where things looked amazing in the viewport but extremely blurry when launching in standalone game mode. So we just want to make sure to check in standalone every once in a while since this is the closest thing to the packaged build and how players will perceive our game. And it also allows us to go full screen by hitting Alt and Enter after clicking into the window. In addition to that, there are a couple of extra settings we need to check to make sure we're running the game at full quality. We can click on Settings on the right and then go to the Engine Scalability settings. This will allow us to easily test different levels of quality, which will usually allow the player to update through an Options menu. For our tests, we just want to make sure that everything here is set to Epic, and also when going back to play in selected viewport, we want to make sure that the screen percentage is set to native or 100%, since if it's any lower than that, the sprites will appear quite blurry. Screen percentage is also often called render scale, and you've probably seen a lot of games which allow you to adjust this setting. This is so that even if you have weaker hardware, you can still run the game itself at the native resolution of your screen to have crisp UI elements, while rendering the 3D elements at a lower render scale to hit your 60 FPS or whatever the performance target is. But for now, we just want to make sure that it's 100% in the multiple places where you can set it and we view the image at full quality. In the project settings, we can look for screen percentage and make sure the manual screen percentage is set to 100%. And screen percentage mode for desktop renderer is also set to manual. And also under editor performance, set the first setting to manual as well and make sure it's set to 100% down here. This setting can also be accessed if we go to the viewport menu here on the left and then we can look at the screen percentage. One additional thing we can do here is set the number to something higher than 100% and this allows us to super sample the 3D image. And you can see how much sharper things get when we set it to 200% for example. But this does come at a rather high performance cost since we're basically rendering the image at 2 times the resolution and then downsampling it into whatever our native resolution is. So let's compromise and set it to 150% for now. This is actually also what Ender Lilies does. It gives the user a slider to set their render scale between 50% and 150%, and you can see a huge difference in quality by just changing this one setting. And I believe with my hardware it actually defaulted to 150% since I have so much leeway in terms of performance. But now we only set it for the viewport and it won't affect our standalone game. Ideally, we want to have an options menu to allow players to set this, but for this quick test, we're just gonna force it through blueprints when the game starts. The best way to do this is probably to create a new game mode and set it as the default in the project settings, maps, and modes. Inside of the game mode on begin play, we can then call the execute console command node and type in r.screen% 150 or whatever percentage you want to use. Now that we're done setting up the screen percentage, we also want to make sure that the actual resolution is set up correctly as well. Back in the blueprint, we can check the current resolution by calling get game user settings, then from the return value get screen resolution, and then print string the result. In my case, it defaulted to 720p, so I want to make sure to use 1080p, which is the native resolution of my screen. Now, before getting the resolution, I want to open up some space and on the game user settings call set screen resolution. Drag off and make int point, in my case 1920 by 1080, but you go ahead and use whatever the native resolution of your screen is. And this is just an easy way for us to enforce a resolution before implementing a settings menu. Now from far away we still do see some aliasing due to Mip Maps, which we'll get into later, but when zooming in it does already look quite nice and crisp. And the same thing holds true for our 2D 3D hybrid scene. Now we're going to look at a lot of different settings related to the texture and how they affect our image quality. First I want to look at the texture resolution of the actual sprite and if a higher texture resolution will lead to a better image. Luckily, the free Cobra robot by Douglas Avila comes with one set of textures for full HD, where a single frame of the character is 713 pixels wide and 588 pixels tall, and a set of 4K textures where it is 1421 pixels wide and 1170 pixels tall. In the texture editor, when zooming in, you can clearly see that the 4K texture looks a lot sharper. But let's see if that also makes a difference in the game, because so far I've just been using the HD texture and not the 4K texture. To test this easily, I simply created an actor blueprint for the Cobra and placed it in the scene, and then created a function that allows me to switch between both of these resolutions, which I then call from the level blueprint when pressing the T key. To make sure the sprite doesn't get bigger though, I had to adjust the pixels per unit setting on the 4K sprite for them to show up at the same size as the HD sprite. Now even on my laptop that has a native resolution of 1080p, I was able to tell a slight difference in quality when being this close to the character, especially around the face. But I couldn't perceive any difference when it comes to the outlines and how aliased they are. And when looking at the characters from further away, I wasn't able to tell any difference whatsoever, so the required texture resolution depends on how large your characters will appear on screen. But when trying this out on a 4K TV, I was able to tell a difference when switching between the HD and 4K sprites. However, it wasn't as huge of a difference as I thought, and it's probably not going to be reflected in this 1080p video. So including 4K textures makes a bit of a difference for players who have a display and PC to support it, but it will have a huge negative impact on performance, so it's something you'll have to think about on a per project basis. Now let's get into some of the texture settings we can adjust. The first one is related to texture streaming, and you've probably experienced this before, that you're playing a game and you see some blurry low resolution textures first before the high resolution textures are loaded in. And this is a functionality that many game engines have to improve memory performance. But for our 2D sprites, this is something we don't want to use since this just looks absolutely horrible and the performance trade-off is not worth it. It's not noticeable when playing in the viewport, but it certainly is when playing in standalone game mode or from a packaged build. To change this and all of the following settings, we want to select all of our character sprites at once for easy editing. In the content drawer, click on Filter and Texture, and this gives us a new filter here which we can then toggle on and off. I keep all of my character sprites in the Paper Assets folder, and when turning the filter on, I can select all of them at once when pressing Ctrl+A. Then right-click, Asset Actions, and Edit Selection Property Matrix. Again, Ctrl+A to select everything, and then on the right side we can make changes to the settings of all of these assets at once. We want to make sure to select Never Stream here to always load these textures in at full resolution. I'm not sure of the specifics, but for this project with these sprites it actually doesn't even let me turn it off, so I already had it checked the whole time. Just make sure it's also active for you as well, and it will prevent blurry, glitchy sprites like this when playing in standalone. Next up is the texture compression setting. A lot of these options here are for very specific purposes such as normal maps, masks, HDR textures, etc., and none of these are relevant to us. There's a great video by Bang Cloud, who is a shader wizard and definitely knows much more about this than I do, which you can check out for more details. But in short, the only relevant options for us are the default, which is BC1 or BC3 with alpha, user interface 2D or BC7. To try all of these out, I just want to open up an individual texture first to see if we can perceive any difference. And no matter which setting I choose and which texture I try it on, I cannot see any difference at all. In Ben's video, which is quite old and still using UE4, you can see a difference when changing these settings, and you can also see how the resolution size is changing as well. None of this is happening for me, so I wonder if the view is bugged or if any other setting is affecting this as well. Using a different sprite in an Unreal Engine 4.27 project, I was actually able to tell a big difference between the default settings and BC7, with BC7 looking so much better while still offering the benefits of file compression. As far as I know, user interface 2D means no compression at all, but I wasn't able to tell any difference between BC7 and user interface 2D. So in my UE5 project, I'll also use BC7 on all of these textures, but you should try for yourself which of these three options best works for your project. When I asked the development team of Born of Bread, they also said they're using BC7 compression. Next up are the Mip Map settings, and even if you're unfamiliar with Mip Maps, you probably know about the level of detail system for 3D meshes. LODs allow us to set up multiple levels of complexity for a mesh and show a lower poly version if the object is further away from the camera. And Mip Maps are a similar system to that, but for textures. Showing a low resolution texture if something is being displayed small on the screen, and showing a larger resolution texture if something is big on the screen. When opening up an individual texture, we are also able to preview all of these different MIP levels that have been created. Here on the right side, you can see the number of MIPs, and this just shows how many levels of detail it can pick from. You can click this check mark and then switch between the MIP levels, and you can see that the resolution gets cut in half every single time. And if we zoom in on a lower MIP level, you can see how blurry the image gets. The benefits of Mip Maps are that we can save on performance by showing a low resolution texture, but also that it helps combat aliasing for textures that are small or further away. In our bulk editor, we can change the MIP gen settings to have an influence on how these Mip Maps are being generated. For pixel art, we don't want to use Mip Maps because every pixel should always appear exactly as it was drawn. And crushing a pixel art image down to half of the size will often completely destroy it. For hand-drawn or high-resolution art, this is a bit of a different story though, and it depends on the case. For our flat 2D scene, if we allow the camera to zoom in and out, it would make sense to allow switching between Mip Maps. But what's more likely is that you have a fixed distance to your character and all of the background elements, and in that case, we could also set the MipGen settings to no Mip Maps. But with this setting, if we zoom in or out too far, you will be able to see some aliasing around the edges of the character, and it will only look good around the same size it was drawn at. So here it's up to you if you want the flexibility of Mip Maps or if you want to make sure the character appears as close as possible to how it was drawn. In the 2D 3D hybrid scene with no Mip Maps, characters close to the camera look good, but further away you can see some aliasing since we're using the full resolution texture here. For the sake of this test, I will keep on using Mip Maps for both the flat 2D and the 2D 3D hybrid scene. But for a flat 2D game, you might also want to try going with no Mip Maps if you know the specifics of what size on screen your character will appear. But now to pick one of these MipGen settings, we need to know exactly what they do, and I found a great blog post by Moko that goes into detail on all of these different options. It's in Japanese, but I'll link it in the attached document, and you can probably use some translation tool to get the gist of it if you want to know more. By default, it is set to from texture group, and this means that it will pick whatever parameter is set on this texture group that we have selected. Texture groups are basically like presets with different settings that can be adjusted, and we'll go into more detail on that in one of the next steps. With the texture group of world, it's actually using the simple average MIP setting. But we now want to manually pick our MipGen settings, and we can choose between these 7 options, with blur or sharpen having multiple levels to choose from. But as you see here, no Mip Maps, leave existing Mip Maps, and Angular don't seem to have an effect. And outside of the no Mip Maps, which we already discussed, these methods are for very specific use cases and irrelevant to us. This leaves us with the simple average we've been using, sharpen, blur, and unfiltered. And you can hover over these to see the tooltip and get a technical explanation of what they do. But let's also have a look at them directly in game. Sharpen is the one that Born of Bread uses to sharpen up the details in the face a little bit, but I'm not quite sure which level of sharpness they used. I tried Sharpen 5 and it appears to introduce a bit more aliasing than Simple Average did. For Blur, I tried Blur 3, and in the case of this character with translucent elements, it made the helmet disappear in the viewport and introduced a lot of blue outlines when playing in Standalone Mode. Unfiltered also just seemed to introduce more aliasing than Simple Average did, and I think which setting is best really depends on your project and what kind of sprites you're using. For both my flat 2D and 2D 3D hybrid scene, it seemed like Simple Average yielded the best results, and I'll stick with that for the rest of the experiment. But for a scene I set up later, I found that Sharpen with a value around 7 helped make characters in the background keep more detail, so you'll probably want to go through some trial and error here after setting up a proper scene. A related setting to Mip Maps is the LOD bias, which has the default of 0. And this allows us to not include the highest MIP levels in our cooked build. But since we of course want to use the highest resolution of our texture for characters, we want to keep this at 0. Next up is the texture filter setting, which is also partially related to Mip Maps. What I've been using here so far and what it defaults to is bilinear filtering, which usually works quite well for high resolution sprites like this. Bilinear filtering smooths out textures by averaging the color values of the 4 surrounding pixels or texels. If you've played any N64 game, then you should be familiar with these blurred out and smoothed over textures, and this was an early form of bilinear filtering using only 3 surrounding pixels. Game consoles before the N64 such as the PS1 and Sega Saturn didn't support texture filtering, and would try to draw the pixels in the nearest relevant place in relation to the texture, which is the nearest setting in Unreal Engine. This is most definitely the setting you want to use for pixel art, since both bilinear and trilinear will completely blur the image. But again, for hand-drawn sprites, it is a little bit different. On the texture preview, when zooming in, you have to pay close attention to see any difference when switching between these settings. But the further you zoom out, the more apparent it becomes that the nearest setting creates aliasing. In the viewport, we can also see that setting the filter to nearest does create more aliasing and instability in the image, and this is also reflected when playing in standalone mode. For that reason, I believe for these types of sprites, using bilinear or trilinear is the better option. Trilinear is basically an improved version of bilinear, where we don't just jump from one MIP level to the next, but it also generates smooth transitions between those different MIP levels. Due to this, trilinear should be superior from a visual standpoint, but will also use up more performance, but probably at a negligible level. But for my tests with these sprites, I couldn't really spot a difference between bilinear and trilinear. Born of Bread also uses bilinear filtering, and that's what I'll also use for both my flat 2D and my 2D 3D hybrid scenes. Next up is the texture group setting, which we just briefly touched upon so far. Texture groups are basically different presets for which we can assign certain texture settings, and there's a config file in every Unreal Engine project with these defaults. And for my character textures, this defaulted to world. In a lot of cases, we already went ahead and overrode the default from texture group with an explicit value. So I believe unless you made explicit changes to the texture groups, there won't be that much of a difference between what we set here. So I would either leave it as world or go for 2D pixels unfiltered. I can't really tell the difference between these, but I'll stick with 2D pixels unfiltered so we can keep a separation between our world textures for 3D objects and our 2D textures for characters. So far we looked at project settings and texture settings, but now we're going to look at a couple of material settings for our sprites. By default, all sprites will use the masked unlit sprite material, and I've been using that for both of my scenes so far. Unlit means that the material is self-illuminating and isn't affected by lights or shadows in the scene. A lit material, on the other hand, would be affected by lights and shadows. What we care about more for the purpose of this video though is the masked part, since we'll have to choose between a masked and a translucent material. Masked means that each pixel is either fully visible or completely invisible, and we can use the opacity mask clip value to decide what the threshold for this decision is. Again, for pixel art this is perfectly fine since we always use fully drawn pixels, but for hand-drawn art using a brush, around the outline we do have this area where many pixels are transparent and neither fully visible or fully invisible. And forcing the masked material to make a decision which of these pixels should be visible or invisible causes some of the aliasing around the character. To quickly try out the translucent material, I'll create a copy of this character by holding Alt and dragging to the right. Then I select the flipbook and go to the material settings. And if you don't see any other materials showing up here, make sure to click on the cogwheel and show engine content and show plugin content, and then we can look for the translucent unlit sprite material. Now on the left we have the masked material and on the right the translucent material. I think you can easily tell that we have less issues with aliasing on the right, but it also introduces a little bit of blurriness or softness around the edges and makes the outline appear thinner. In the hybrid scene I did something similar, again using the masked material on the left side and the translucent material on the right side. The most obvious thing is that we can now see the glass dome on the spacesuit properly since all of the different opacity levels are properly represented, while on the left side the glass is completely invisible outside of the specular part. But having transparent parts like this on your 2D sprite is quite rare, and it's not what I want to really focus on here. But I do think the outlines also look a bit smoother and cleaner with the translucent material. When making a flat 2D game, using a translucent material also allows for things such as sorting layers by priority levels you can manually set, so that alone might make you want to use it for those purposes. But generally speaking, translucent materials do come at a higher performance cost than masked materials, and there's a great video by Unreal Dev Hub going into detail. which I'll also attach in the linked document. However, especially for flat, unlit 2D games that don't have any lighting in the scene, I think the difference is probably negligible, and I think for those cases a translucent material is definitely a valid choice and it's something I've used before. But for 2D 3D hybrid, things are a bit more complicated. In most cases, we do want lights and shadows to affect our characters, so we want to use a lit material, and to demonstrate I'll switch from using the unlit material to using the masked lit sprite material on the left and the translucent lit sprite material on the right. I'll then set both of them to cast shadows and place a cube in the scene to demonstrate the lighting and shadows. Even though the translucent material looks crisp and has less aliasing around the edges, it is unable to cast shadows, looks very dark, and while it does receive shadows, in a way it's very blurry and imprecise. The lighting is the only thing that appears to be working properly here. Now, I've never been able to get a translucent sprite material to play nice in these conditions, but if you had more success with this, definitely let me know in the comments. So for now, I don't think the translucent material is a good fit for our 2D 3D hybrid scene, and I want to instead concentrate on improving the masked lit sprite material for a scenario like this. To be able to adjust the properties, I first want to create a copy of the sprite material that comes with Unreal. I can find the material in the character and click on the folder icon to find the source. Then I don't want the instance, but the parent material and drag it onto the content folder and then copy here to create a copy of it. I then create an instance of this for easy editing and make sure all 3 of these flipbooks are using it so that changes will be reflected. In the parent, I just double check that the blend mode is masked and the shading model is default lit. In the material instance, I can then look for the opacity mask clip value and try out different values. Again, to reference Born of Bread, they said that they're also using a masked lit material and had to adjust the clip value a little bit. Since we have a pretty rare case with the glass material on the helmet, I had to go all the way down to 0.1 to make it appear. And I feel like this also made the outlines appear less aliased and quite sharp, and I'm pretty happy with the result. In the flat 2D scene, I then created a copy of the masked unlit material the left sprite was using and also changed the opacity mask clip value to 0.1. And while the difference here is very slight, I still believe a lower value gives us a slightly stronger outline with slightly less aliasing. But again, for these flat 2D games, you might want to stick with the translucent material on the right, and the choice is up to you. And on a side note, when then using your sprites with a character blueprint, you'll most likely want to change the pixels per unit setting to something large like 2.0 or 3.0 to match the size of the capsule. This way we shrink down the sprite, and it's pretty much the opposite of what we do for pixel art, where we use a value smaller than 1 to make the sprite bigger. Roughly matching the size of the capsule just makes sure that the settings in the character movement component are correct, and that our character size is compatible with all of the maps that you're going to find on the Unreal Engine Marketplace. Now, to close things out, there still is a deep rabbit hole about signed distance fields and the smooth step material function that I'll briefly touch upon at the end of the video, but all of the settings that we've gone through so far are the settings you usually want to look at, and I think that even commercially successful Unreal titles like Born of Bread, The Vagrant, and Ender Lilies achieved their look for the most part by adjusting these settings and finding the values that work best with their assets. They might not look absolutely pixel perfect, but the players won't notice unless they hold a magnifying glass up to the screen, and it's a non-issue. So before looking down the rabbit hole, let me just sum up what I found to be the best settings for both the 2D 3D hybrid scene and the flat 2D scene in my case. We turned off motion blur and eye adaptation, turned off Lumen, virtual shadow maps, and set the reflection method to screen space instead of Lumen. We used FXAA anti-aliasing for both scenes since it doesn't only help combat aliasing on the background elements but also the sprite's edges. We made sure that the scalability and screen percentage settings are at the highest level of quality, and we also confirm all changes in the play standalone game mode to ensure that we see it as close as possible to what the players are going to see. In the same vein, we also made sure to set the resolution to the native resolution of our screen and play at a screen percentage or render scale of 150%, and when packaging a game, we should have an option menu to allow the player to influence this setting. In the texture settings, we check Never Stream and use BC7 compression. For the Mip Maps, I found that simple average or different levels of sharpen worked best for me, but in your case you might also want to try out blur or no Mip Maps depending on what kind of project you're making. For texture filtering, I stuck with bilinear, but trilinear might also be a valid option, and we could expose that choice to the user as well. Texture group wasn't all that relevant since we overrode many of the default settings, but I stuck with 2D pixels unfiltered so we can keep our sprites separate from the 3D objects in the world. For the flat 2D game, using a translucent material was a valid option that combats aliasing around the edges, but makes the outlines appear a bit blurry and quite thin. Alternatively, you could also go with a masked material and adjust the opacity mask clip value to your liking. In the 2D 3D hybrid scene, the translucent material also seemed fine when using an unlit material, but didn't work out quite that well using a lit material, which is most likely what you want for a game like this. But by again adjusting the opacity mask clip value, we were able to fine-tune the outline around the sprite a bit and also made the glass part of the helmet visible. That's pretty much it, and I think the result looks quite nice and should be good enough for most cases. But if you want to improve things further, you might want to look into signed distance fields. I'm only going to briefly touch upon this, but the first time I even heard about this was when watching the 2D characters in 3D World and How I Improved Them video by Jay the Deaf Guy. His main concern wasn't about the aliasing around the edges of the character, but also the dark inlines on the character becoming blurred when the sprite is very close to the camera, no matter how high the texture resolution is. In his video, he gives a great introduction to the topic, and I definitely recommend that you check it out, and there are also a few very technical articles explaining what signed distance fields are and how they work. But in short, signed distance fields allow us to understand the distance between an object and its edge, and we can use this to create an even cleaner outline around the character without any aliasing. Jay the Deaf Guy used a normal map and the smooth step node to achieve this, but there are also other methods, and Tanoshi from our Discord put together a document with their methods of implementation. After just playing around with it a little bit, I couldn't see that big of a difference, and really dialing in on the correct values for a sprite with this will probably take some time. So since I was already happy with my result regardless, I didn't push it further, but you can definitely go further down that rabbit hole if you want to. All mentioned videos and sources are again linked in the document below. I believe this should cover the majority of settings related to high-resolution sprites, but if you have any additional knowledge or something to add, feel free to write a comment or join the discussion on our Discord. A huge thanks to all of the people in our Discord who looked into this, Jay the Deaf Guy for his video, and also Wild Arts Games for sharing their settings. And as always, a big thanks to my awesome patrons and YouTube members.